Okay, so let's get started with, as usual, the summary of last week. So last week we had two different topics. One was looking into series expansions, and the other one was mean field. So we looked into exact solutions of the 1D Ising model by series expansion, and then particularly focused on the partition function, which in the series expansion is defined as beta j to the power of the number of bonds, summing over the states. This is the high temperature. High temperature series expansion, multiplication of the neighbors plus SI SJ V. And then we saw what determines the partition function is, in fact, if our 1D, oh, someone's taking over. Thank you. If our chain is closed or open, and so this changes the value of this factor, it's 0 for an open chain, because there's then no closed loop that I can sum over, or it's exactly v to the power of the number of sides in my closed chain, which actually constitutes the only closed loop that I can form. And then we unfold the power of this series expansion by looking at the correlation function, which we found to be to the power n cos h beta j to the power of the number of bonds normalized by the partition function. And then the difference is that now this spins pop up, and so they change then which chains can contribute, because we're looking for even exponents, right? And so all of a sudden I can have even exponent as if Si is equal Sm and Sj is equal Sn, which means that I can also, for the open chain, I can have a loop that's contributing here, which is going from m to n. This is for the open chain. And for the closed chain, I can have the same loop, but since it's closed, I can also have the contribution of looping the other way around between these two spins. It's a closed chain. And then we went on to look into the concept of duality, self-duality in this case, in the 2D Ising model on the square lattice. And we saw really how symmetries unfold by writing down the high and the low temperature expansion. So the low temperature series expansion actually amounts to counting the parameters of spin flip islands. Spin flip islands, while the high temperature expansion amounts to counting curves in 2D with 2 or 4 lines per lattice side. And so if I draw this for a 2D lattice, say I have this spin flip islands in an ocean of passes, then, and I want to find I mark the parameter of the spin flip island. It would be this one, and that's in this case also for the 2D square lattice is also a curve that I would count. Actually, curve we call it graphs. Graphs. This is exactly. Oops. This is also a graph that I would that would contribute because it exactly has 2 lines per 2 or 4 lines per lattice side. So there's a 1-to-1 correspondence, and actually the series expansions could be mapped to into each other because of the self-duality, and that amounted to mapping e to the power of 1 expansion to tangents of the coupling constant of the other expansion. And then we realized that since we now sort of mapping coupling constants onto each other to find the opposite expansion, at criticality, we would expect divergent behavior like an instability, and this can only be this only makes sense if at instability, at criticality, this mapping, they're mapping onto each other. So the critical temperature we here could then derive from e to the critical coupling, which is related to maps like this, where Kc is 1 over kBTC times J. So that was the example that showed us that we can, with series expansions, use dualities, and we try to look at that in the context of the dual of the 3D Ising model on a simple cubic lattice. But here we found that what we need to do to find a dual of the Ising model on a simple cubic lattice was to define, if this is my lattice yet again, these are my lattice sides. What I would do is I would define now spins on the bonds of my lattice, and I would couple them together in so-called plaquettes. Their corresponding Hamiltonian would then look like summing now over these plaquettes, which are coupling 4 spins together within these plaquettes. That would actually allow us to recover the low temperature terms of the 3D Ising model as high temperature expansion of the plaquette Hamiltonian. And so we found a dual and used this example to dig a little bit into symmetries, because on first side, the idea that we have order at final temperatures is conflicting with Elizour's theory that states that I can't have spontaneous symmetry breaking, spontaneous symmetry breaking, which is required for ordered phases, with a local symmetry, which we would have because in these plaquettes, if I change two spins at the same time in direction, the plaquette Hamiltonian doesn't change its value. And there was a rescue to that as well. So that was the first part of last week, and then we started looking into mean field theory, which we will continue today. The idea being a variational approach that I want to find the free energy of a system given by Hamiltonian H and approximate that by a variational function phi, which is given by the free energy of a simpler Hamiltonian H naught and the difference of the real Hamiltonian I'm interested versus the simpler Hamiltonian evaluated in the ensemble spanned by the simpler Hamiltonian. So this here denotes the average taken over ensemble, yeah, defined by H naught, and that's the so-called Bogoliubov. I did not practice. There we go. And so now we can even refine this method to define the so-called mean field free energy as the minimum of this function minimized with respect to a parameter H naught that's part of my simplified Hamiltonian. So that's the mean field free energy. And then we applied this concept to the Ising model. Where, just to recapitulate, we have a Hamiltonian where we have some interaction and an applied field, and then our simpler Hamiltonian is the one without interaction, which is identical to the Hamiltonian for paramagnet, which consists just of the second term. And here now our H naught has the role of being the parameter with which I'm minimizing my function to find the best estimate of a free energy. But from conceptually, the way I'm writing this down, there's very deep insight, because what I'm actually saying is that I'm approximating this full system by a system where the spins don't interact, but the field that is acting on each spins is given by H naught. And H naught here has the mean field, like a mean magnetic field. Mean field is the mean field. And so minimization of phi with respect to H naught leads to the expression H naught is equal H plus J beta H naught, which is the defining equation for the mean field, although in a sadly explicit form, implicit form, not explicit form. And notably, this is exactly the same as we can identify this second term as being the average spin. So what is actually stated there is that the mean field is, sorry, H plus J coordination number S. But it's already very insightful to have this condition on the mean field, because we can now look for solutions of the mean field according to this equation. And so the graphical solution to that is to plot the function as a function of H naught. And so, so that would be H naught, like the linear curve. And then if I plot this function, and this is actually for H equals 0, I can have tangents that have, sorry, not ideal, where I find that there are all of a sudden 3 solutions. And so I have a spontaneous mean field magnetization at a temperature below a critical temperature. And if I increase the temperature, that would be T at TC, this additional crossing vanishes. And don't quote me on the vertical lines, T bigger TC. So I find a phase transition. Ta-da! We're very happy because all of a sudden we found one, given that this was the whole scope of this class, to find phase transitions. And we could even determine from this graphical solution the critical temperature, namely TC is Zj over KB. Also going to use quite a number of time today. But we were also very sad to realize that according to this mean field approximation, we would find a phase transition also for the one-dimensional Ising model, because the only quantity that determines the critical temperature that is somewhat dimension dependent is this coordination number there. But the coordination number is still finite for D equals 0, for D equal, so for a one-dimensional Ising model. So the mean field falsely predicts a phase transition also for the one-dimensional Ising model. And we realized that the assumption of this mean field approximation is only a good assumption if a spin has a lot of neighbors, so if my coordination number is very big. So mean field. Good. And this actually also to state, so this is the mean field is acting and it corresponds to the field that is applied. And this is the second term is really the field that's now generated by the neighboring spins. And so only if Z is large, this is really representing for each individual spin the average field, because if the number of spins that are my neighbors are large, then actually the spins that a spin is sampling in its neighborhoods correspond to the ensemble average spin magnetization. Mean field. Okay, and that allowed us to derive the first mean field critical exponents for the Ising model. And so we write this in terms of this reduced temperature small t, which allows us to which allows us to expand our results in limits of small t, because we're interested in what happens at the phase transition. So when t goes to 0. And here we find that the mean magnetization of a spin is given by either 0 for t larger than 0, so above the critical temperature, or square root 3 minus t to the power of half for t smaller than 0. So graphically speaking, the magnetization, oh God, looks like this. And so we find that here actually this magnetization serves as an order parameter, because it's different for every phase, and thereby allows us to determine in which phase we are. That's a quick recap of last week. And now if we go forward with the content of today's lecture 10, we will continue with mean field theory and do more critical exponents. The Ising model. We're gonna look at the Helmholtz free energy, all mean field, and then take a discussion into why are we interested so much in these power laws, and what does it mean for a power law to be scale free. So power laws means this one, right? Value to the power of a function. Okay. So for questions? Okay, because this is going to serve as our cheat sheet for today. There are many more critical exponents that we now can calculate. And we start with the magnetization of for the non-zero field H. So remember, our equation was that it's defining our mean field was Zj tanh H beta H naught. And so what I can do, I can multiply this whole equation by beta to arrive at this equation. And then I can take tanh H and remind myself that we had the mean magnetization being given by tanh H beta H naught. So we can see that if we apply the tanh H on the left-hand side, we can recover the mean magnetization of the spins. And so we get S naught is tanh H on beta Zj. And I'm also replacing this tanh H beta S naught plus H. Now we are interested at the magnetization for a non-zero field at criticality. So we do know the critical temperature. T is equal to Tc, and that means that I have beta T I can write as Zj. beta is 1 over zj. So that simplifies my above equations to now these two terms cancel, so that I have just s, and I can also write beta times h as h over zj. Now, to find a scaling relationship, I have to expand again. And since I'm interested at the behavior at criticality, where we know the magnetization starts growing from 0, we expand for the magnetization to be small, and we also have to assume the applied field to be finite and small. And then we find for the right-hand side the following terms. And again, as discussed this last week, we are careful and we state the order of the next higher order terms that we are neglecting, so we can check later on that indeed these terms here, these terms are indeed small for the result that we get. Self-consistency check, which we need to do because we're expanding for two variables being small, which can lead to mayhem. Okay, so this is nice. This term cancels, so I can rearrange the remaining to find that S naught actually scales like 1. Oops, no, the most important thing, over 1/3. Yet another critical exponent. So, and this translates in critical exponents. This is defined as defining this variable delta equal 3. Graphically speaking, this means that S naught as a function of h looks and hitting the zeros, something like that. And again, we can check that these higher order terms like S naught h, they would here then scale as h to the 5/3. So they all are indeed higher order to h and s cube, which is this term, right? Which scales like h as well. So indeed the higher order. As are the other neglected terms. Okay, what we're really interested, remember, were these response functions. So the magnetization, we expected discontinuity, which we found as a first order derivative of the free energy. We also were really interested in these response functions. And there are two of those. One is the susceptibility and one is the heat capacity. So let's turn to them one after the other. So the susceptibility at criticality, I believe, which I noted was nicely in Yeomans. So the susceptibility is defined derivative of the magnetization with respect to the applied field at constant temperature, which in our case means the magnetization is the average spin, dH. And this describes at a criticality, a divergence in the response function, in this case of the order parameter, to a field, the applied field, that it is conjugate variable. Okay. So again, we have to now take a derivative of the magnetization as a function of H. We start with this equation, but we're gonna, no, we're not this equation, because here we assume to be at criticality. We start with this equation because we're interested in how we expect to have a divergence at criticality, so we don't want to jump at criticality, but we want to look at how do we approach criticality. So we go back to this equation, and we remind ourselves of the definition of the reduced temperature, which was that we had that as 1 plus T. And so if I now plug this in here, I can write this equation as and then plus H over JZ 1 plus T. Okay, again, implicit equation, and so we expand for H, T, and S naught small, which looks very similar to the above expressions, rearranging to find that we can write the field as T as naught. What we're interested in is to find the derivative of the magnetization with respect to H, right? And so we, neglecting the higher order terms, we in expanding this equation, we arrived at this expression. And if we now take the derivatives with respect to the applied field, we will get these derivatives in a functional form. So we apply this, we get 1 over JZ here, T. Here we get our response function already. Let me just quickly abbreviate this as with our psi already. So this is our psi, and then we get here 1/3 S squared psi. And so we can rearrange this as T plus these two cancel. Times psi. And so that's, we can rearrange as 1 over JZ T plus. Okay. And now we know the behavior of the magnetization at criticality. And so we can now look at the two limiting cases, again, going back to our cheat sheet from today, which was, remember, we had the magnetization being 0 above the critical temperature and scaling like square root 3 minus T to the power half below criticality. So if we plug this in here, weakened. So for above critical temperature, that's just a T. So that means I have 1 over KB T minus TC for T larger 0. And here I get this square root, which there's a square here, which means I have this. And this is actually renowned as the Curie-Weiss law. Graphically speaking, what this means is if I plot the susceptibility as a function of temperature, this being the critical temperature, then below the critical temperature, I diverge like this, and above the critical temperature, I diverge like that. Note, however, that the scaling that I have for would be with respect to the reduced temperature that we denote as T to the power of minus gamma plus or gamma minus, like the critical component exponent gamma, in principle could be different. Like in principle, a priori, we could have gamma minus unequal gamma plus, but here we do find that they are in fact the same. In practice, is equal gamma plus, and that's a 1. Another critical exponent. Okay, so that's the one response function that we're typically interested in. And as I said, the other one is to look at the heat capacity at criticality. And so that's defined as minus T, and now explicitly stating the second order derivative of the free energy with respect to the temperature at constant field. This is now the thermal response function. So now we got really away with just looking at expansions of this defining equation of the mean field. But since we here now have to take the second order derivative of the free energy, we actually have to go back and write down the mean field free energy in this case. So remember, we had defined the mean field free energy as F naught, this being optimized H minus H naught, sum over H naught, and this is minimized varying H naught, which gives our condition that this is minimal for H applied H naught is applied P plus Z jet S naught. And so if we now write down this mean field free energy in full length, we arrive at there's a minute. So this is the free energy of the paramagnet. H And then these are the terms arriving due to this second term. We had them written down when we looked to find this expression, which I can simplify these two later terms as minus kbt and okay. And now, as before, we don't want to deal with these logarithms. So we expand for magnetization being small, H being small, and the reduced temperature being small, and then express our results again in terms of the temperature, not the reduced temperature. Since you've seen a lot of expansion already, and I did check them. Which doesn't mean anything, you can still check them. We arrive at nkb T minus Tc. Should circle that one. We're going to see this one again. Oh, wrong color. We're going to see this free energy result also popping up again when we look into the Landau-Ginzburg, whatever, theory, where we derive Hamiltonians based on symmetries. So notably, we here have a constant term that we don't care about anyway, because only, you know, this is just an absolute shift in the energy. We have the applied field coming in here, and then we have, with respect to the magnetization, we have a quadratic term and a quartic term popping up, where yeah. So these are the terms that we will find again. But here they just follow from the mean field approach and expanding this expression in terms of the mean field, the applied field, and a reduced temperature being swap. Now we are interested in deriving the heat capacity, so we want to take the derivatives with respect to the temperature of this expression. To make our life a little easier, we are going to use that we are interested in the behavior at criticality, so we can already assume the behavior at criticality that we do know for the magnetization. So we know that above criticality, we have the mean magnetization being 0. And so that means that this term doesn't exist, this term doesn't exist, this one doesn't exist. So actually the free energy is just a constant. A constant, you know, it's just linear in temperature. And so if I take the derivative twice with respect to the temperature, this vanishes. So we find then that d squared mean field is equal to 0. Okay, so the more interesting case obviously pops up for being below the critical temperature, where S now scales as square root 3 minus T. Sorry, it's notation. There we go. Half. Which I'm going to write as T minus TC over TC. And so in this case, what we need to do is to take the second order derivative of, okay, and now let's just plug it all in. So here we have a square, so we're squaring this one, so we get 3 over 2 n KB. Then we have a T minus TC here, and we got another T minus TC over TC popping up from the magnetization. Then we have a quartic term to the power of 4. We get 9 over 12 n KB. There's a TC missing, and then we have T minus TC over TC squared. And n square root T minus TC over TC. H. Okay, so what will happen is, okay, simple things first. Again, this is the linear term. If we take the second order derivative, this will vanish. It's easy. If we look at that term, we're interested in the thermal response function at 0 applied field. So at 0 applied field, if we set h to 0, this term vanishes at h equals 0. So we only have to deal with the first two terms that we can simplify by noting that this is 3 over 4. And we in both cases, we have a quadratic dependence on the temperature T here and there. And so if we take the second order derivative, both terms prevail, but they're gonna lump together because they have the same prefactors to arrive at, in the end, 3 and, oops. Uh, 3 and KB 1 over TC. So we find that the heat capacity is then given by minus, oh, sorry, 3 over half. Minus 3 over 2 N KB T over TC below the critical temperature. So indeed, we now compare this, maybe I should state this here. So the heat capacity is 0 above the critical temperature, and it's equal to this value below the critical temperature. And if T is equal to TC, this is a finite non-zero value. So we do, in fact, observe a jump in the heat capacity. And in the meantime, we identified another critical component, exponent, namely this one is defined as scaling with the power of alpha, so this is alpha equals 0. Okay, so this is like the fast forward through, hey, we can actually calculate critical exponents now with the power of the mean field theories for the Ising model. And we already saw for 0 applied field how we can see that there is a phase transition. And what I find really appealing about this graphical solution of the constituting equation of the mean field here is that you can readily read off the dynamics of the system. And in the same fashion, I will now derive the Helmholtz free energy, which allows us to also nicely read off what happens at phase transitions at finite applied field. Yeah.
Question. It's just I'm kind of confused why the heat capacity is negative. Like, is it natural? I mean, maybe I just don't see it, but I thought it would be positive.
It's defined with a minus sign. Did I lose the minus sign?
No, you like inserted the minus sign at the end, which was
no. It's this minus sign here. It's I multiplied by minus t. So we derived the second order derivative.
Yeah.
And then applied my minus. Multiplied by minus t.
Yeah.
And that's the difference between this equation and this one is the minus t.
But I'm just confused. Was the heat capacity always negative? I thought it was always positive for some reason. Like the heat capacity is positive because it's kind of related to the heat fluctuation, the energy fluctuation in the system. So it should be positive, right? So I'm like incredibly confused why it's negative. Like what's it called? The fluctuation dissipation theorem or something like that, where you related the response function to the fluctuation.
See what you're confused about, but does anyone have quickly the cheat sheet? But I believe that the definition that I used here is what's the first lecture? October 8th. Is this where we have the cheat sheet? No, oops. Yeah, no.
That's just the first one, right?
Lecture 6. Here we go. There are actually. So there is no minus sign. I don't know how the minus sign popped in. Okay, so then we rescued it. Okay, good. So that's why we have cheat sheets. I don't know how it came up here. But if there's a plus up there, that's how the minus can come up. This was just from the definition that I apparently falsely copied. Maybe, look what happened. I mixed up the specific heat with the susceptibility, and the susceptibility has a minus sign here. Thanks so much. Yeah.
And it is also because of the stability. And
no, it has to be like, you're right. Okay, yeah. And so now the idea is we go for the Helmholtz free energy because again, it's a nice way of how you can see a graphical solution. And why do I put so much emphasis on graphical solutions is that even if you are not able to find an explicit analytical solution, a graphical solution, like just plotting the Helmholtz free energy actually tells you what will be going on in the system, even though you can't write it down in an explicit equation. And so that's the power of that. And so we turn to the mean field Helmholtz free energy here following Schwabe, chapter 6. Okay, so mean field Helmholtz free energy that goes with this letter A is defined as the free energy plus magnetization and applied field, which in our case means that we're going to use the mean field free energy that we had above, plus our magnetization being the number of spins we have in the system and the average magnetization H. Note that this is another standard notation, right? The small m is another standard notation for the magnetization per spin, and then the capital M is the magnetization of the entire system. Okay, and so if we just copy down this again from above, this term. And now we're adding this extra term. And we again go at criticality, so we know that I will write this as 1 over kbt, and this is again 1 over kbt. I will rewrite this as tc times kb, and also here tc kb over 2 using the critical temperature we identified to rearrange then I can pull out a 1 over t, and I've left h over kb plus the kb here cancels, so I only have tc and the magnetization per spin left. And that's tc kb n over 2 plus n s h. Okay, so this we still need to simplify. Yeah.
Could you say something to the very first line?
The first line? Okay, so this is the mean field free energy from
The line above.
the line above. This one.
Yes.
Oh, this is the definition of the Helmholtz free energy. Like this is one of your thermodynamic potentials, and it's defined by the Legendre transformation of the free energy. So that this is one of the potentials that you arrive at.
I think you're just confused about plus. It should be like an equal sign after the NH.
Ah, okay. Sorry for that. Yeah, no, that's just a simple typo. Yeah, there we go. That makes sense. Thanks. Okay, so we want to simplify that one. So, okay, just because we're switching notation a lot, so this is actually again the constituting equation, right? Of the mean magnetization. And what we're going to do now is like to simplify this term by using a lot of trigonometric identities. And use namely tan h squared x is 1 minus cos x of 2, which means that 1 over 1 minus squared. And so that means we can rewrite this hyperbolic cosine as a function of tans of this variable, this expression, and tangent of this variable is exactly our mean magnetization. So that's the trick we're using. So then our ln 2 cos h, just copying down. Then becomes, let me factor out this ln2, ln of 1 minus tangent squared which is going to, I can pull out the half up front because we have logarithms here, and then I pulled out the minus sign because I'm going to invert the, I'm going to multiply with to the power of -1 to put the 1 minus tanh to the top, so that I have in fact just a 1 minus magnetization squared. Much simpler. And then we're going to further use that the inverse tanh is defined as 1 minus ln plus x over 1 minus x. That allows us to reorganize this expression in the following sense, that I can now say t maybe and that's nothing else but 1 plus s naught 1 minus s naught. And so we then arrive at we now solve this expression for the applied field H. We get half kBt ln 1 plus just 1 minus field, and the second term kbtc. Okay. And so then we can use this, what we derived here, to simplify, put this into this term, so that, and we simplified this term, not doing any expansion, right? No, we didn't do any expansions. We just rewrote this with trigonometric identities to this term. So if you put everything together, we get, and I'm going to normalize it by kbn. So we have the minus t ln 2, which is coming from this term. And the second term is then a half t ln minus s. And tc over 2. And then these, this is this term, right? And now if I plug in this relationship I found for the applied field, we get minus tc s squared plus t plus s. Doesn't like me because I'm too far close. There we go. Okay, and this we can, these two terms become minus tc over 2 squared. Otherwise I have like a closed expression expressing now the Helmholtz free energy just in terms of the magnetization. And in principle, I can now plot this function as a function of S and see while I'm varying my temperature with respect to the critical temperature, what different behaviors do I get from the function? And so this is what you would do if, you know, this was your research project, and this is what you would arrive at as an equation. I believe it's pedagogical in the setting of this lecture to not like start whatever Mathematica or MATLAB, but rather actually do expand these terms so that we see which functional form is actually hidden behind these logarithms. So if we now look at this term while we send the magnetization to 0, we see that this can be expanded as a half t to squared minus and similarly this term becomes t okay, so what we see now is that we have a term that's independent of the magnetization. We have quadratic terms, and we have the quartic terms. The quartic terms I'll expand to put them on together so that we find that this is minus t and 2, and then we have a half, oops, t minus tc quadratic term plus 12t. Again, note that also in the Helmholtz free energy, we have two terms governing our dynamics. One is quadratic in the magnetization, one is quartic in the magnetization. We will see this again when we do Landau-Ginzburg. What we notice if we look at this simplified expression now is that what we're varying when we're approaching the critical temperature is actually the sign of this term, right? So for above the critical temperature, this is positive, and below the critical temperature, this is negative. So the only dynamics that are like changes that are happening is because of the change of this prefactor. So this changes sine at t. And so graphically speaking, what this means is the following. If I now plot A over K B N plus T ln 2 as a function of these terms, then I find that maybe I do this green thingy again. So yeah, all prefactors of okay, yeah, kind of. So above critical, yeah, you can see this. Temperature, all terms are positive. If I approach these terms becomes 0, so I'm governed by the quartic behavior, so that's a little like flatter here. And then below critical temperature, what happens is that I dip and this is my functional dependence. And so since the system will attain the state of minimizing the Helmholtz free energy, we find that above the critical temperature, at critical temperature, there's only a zero magnetization, but below the critical temperature, I have an m naught minus m naught defined by these two minima, which correspond to a spontaneous magnetization below critical temperature. And so this is the so-called Mexican hat that you see here. The hat, whatever. And so now what is cool is that here we can really read off the magnetization graphically speaking again. So because since my Helmholtz free energy is 3 NSH, I can write the field as KB DAN over KB, taking the derivative with respect to S naught. And then the magnetization as at a given field can graphically be read off by drawing a tangent of slope h over kb to the function a over n kb. And so if I do this, then I find for the monotonically decreasing and monotonically increasing function below critical, above critical temperature, there's only a unique solution of drawing such a tangent. So for, I find a unique solution, but below critical temperature, if we find these tangents, and now we are lowering the applied field, then at h equals 0, we will find two solutions for the minimal free energy. But in general, we can find a solution also for any given applied field. And also this will have, we'll be able to read off two solutions. We keep lowering h. And so what this tells me is that both are equally likely, right? So I will have both regions of magnetizations of M and minus M naught, of M naught and minus M naught, being present at equilibrium. So what I will have is that, in fact, I at below critical temperature, I can have regions of spins all being at M naught, and I can have other regions of spins all pointing into minus, having a magnetization of minus M naught. So regions of magnetization, M naught and minus M naught. To each other. And so say fraction C is M naught in my entire system, and then correspondingly a fraction 1 minus C is at minus M naught, then the total magnetization is C M naught plus 1 minus C minus M naught 2C minus 1 M naught, which is in between minus M naught and M naught. And so note that all these A of M naught is always smaller than any other magnetization, yet we find no homogeneous state with magnetization M. Instead, domains of magnetization minus M naught and M naught, analogous to the Maxwell construction of the van der Waals fluid. And I'm going to briefly skip the entropy of the mean field and to have time to discuss why we care so much about these critical exponents being power laws. Or short, why are power laws so-called scale invariant, and what is it, scale free? Same thing. And why do we care about this? Okay, so what we're doing here is, first of all, when we're looking at critical exponents, there are only dimension less variables to be raised to an arbitrary power. So that's why we, for example, use the reduced temperature, which is a non-dimensional. So that's the first ingredient. But yet, what does it mean that if I take t to the power half, that makes it scale free? So yet in what sense is a power law more scale free than, say, an exponential? So let's consider this. Let's consider we have one function where we're raising a variable, like say a length scale that we normalize by a typical length scale of a system to a power, and we compare this function versus f2, where we're looking at the exponential of, again, a length scale, a variable of dimension length normalized to make dimensionless by a typical length scale of the system. This is a scale. So to visualize this, consider that we will consider the values of these functions subspaced in different ranges, 3 different ranges. The values. And so we'll space them out to be centered at R0, 10 times R0, and 100 times R0. And so how do we define the ranges? We define the ranges to be each a factor 2 down and up from the center. So this is just 3 different ranges. So for R0, we go from half R0 to 2 R0. It's one range. And similarly, we have a half 10 R0. We go up to 2 times 10 R0, and so on. And now we're gonna look at the ratio of the largest and smallest value of this range by evaluating them once with the function f1, which is the scale for 1, compared to our expansion. So the ratio of the largest to the smallest value in the range then is for f2, so for the exponential, we have so we plug in 2 R0 for the upper limit of our range, so that gives an exponent of 2, and then the lower range, which gives an exponent of a half. So what we have is then e to the 2, the upper limit, the ratio compared to the lower limit, which is e to a half, which I can evaluate as e to the 2 minus a half, and that's just e to 1.5. And similarly, I can do this for the other 2 ranges. Again, I get then 20 minus 5, so that gives me e to 15. And for the largest, for the range centered around 100 R0, I get e to the 150. Now the magic is that if I do this for the scale-free function, what I have then is I take 2 to the power of eta and divide by half to the power eta, and that's just nothing else than 4 to the power eta. But if I do this for the second range, then I have 20 to the power of eta and 10 times a half to the power of eta, and let me actually rewrite this: 2 to the power of eta, 10 to the power of eta, and you see that then these cancel out, and I arrive again at 4 to the eta. And that's also true for the largest one. So independent of the choice of my range at which I look at this function, I find the same ratio between the upper and the lower limit. And what this means is now that I can superimpose the functional dependence by just rescaling with a simple change of scale. So the ratio is independent and only depends on this parameter in itself. So the three graphs of F1 can be superimposed by a simple change of scale. And so this means that in this sense, a phenomenon obeying a power law looks the same no matter on what scale you look at it. And so the reason why this power law phenomenon, if you have systems that obey power laws, really got a good portion of the statistical physics community crazy at one point, is the connection that what is the origin of having the scale free behavior, and that's criticality in the end. Because what so it's the origin of scale invariance or scale free behavior. It's the same. It's that you have these long range correlations, which you have with criticality relations, which may make your system appear similarly if you look at short length scales or at large length scales. So maybe you remember this image of the spin magnetization at criticality, where you could see that if you take the whole lattice of spins popping up and down, but if you just look at a quarter of this entire lattice, it would actually be a self-similar image. And the divergence of these long-range correlations, because of the correlation dissipation theorem, map again then to the divergence of a response function at a critical point. These are linked to correlated fluctuations over long distances. And so sort of on this meta level, there was a business, and I think it died out now. I would hope it died out now, but sort of like still in the 90s and the early zeros, the statistical physics community was basically looking at various systems and try to see, are these scales free? So to take an example, if I look at the statistics of earthquakes, right? If I take the statistics of earthquakes and how they scale in time, not in length, but in length scale, but now it's scaling in time, is this scale free behavior? whatever, look at the size of ice shelves in the Arctic, right? If I measure the size and the plot is the scale-free behavior. So and the word of caution to say that, and then if it were scale-free behavior, then it would tell you that the system is at criticality and it has fascinating physics behavior. The word of caution to have there is to drive home that the system is really scale-free. In this example, we looked at very large ranges. So I on purpose took an example that the system is scale-free over 2 orders of magnitude. And this is what you should take if you ever jump into this field, which is called self-organized criticality, which was pretty much in vogue in the 90s and zeros. That you only have a critical phenomena if you really can show that it's scale-free, at least over 2 orders of magnitude, which honestly, typically you don't have the data. And like in lots of cases, you don't have the data for. And so any claims of a system like distribution of earthquakes being at criticality should be looked at with a questionable eye. I mean, just as a word of caution, connecting all this insights to using statistical physics to study very broad range physical systems. And with that, I'm closing for today, and I thank you for your attention. Thanks.